can cover the majority of what we need to, because our final is actually May 1st, and based on what we've gone through so far, I would rather wait a couple more weeks. So it'll be April 15th. So I changed that on web courses.
Didn't receive the other one. So I could have submitted the last one. They did submit the other one. They got something. I had used that straight. Yeah. My grades would drop.
Alright, so we're going to do a little more big O analysis, and should be moving on from there. Don't forget, tonight is Wednesday, so at 2:30 room, HPA 116 is the second review session for the foundation exam. Alright, so we started talking about Big O last week. And then we kind of like skipped over after notations on Monday. So Big O is a Big O notation, and so it's just how efficient is our algorithm. So we quickly went through how we can determine, the biggest impact on the, from a function. And so what we want to do is we just want to, we want to know the performance of an algorithm as that responds to our changes in the problem size. So today we're just going to go over some examples of analyzing the code. And so each of these functions is analyzed for their the runtime in terms of the variable n. And we're going to use the concept of Big O to determine the runtime of each one. So here's our first example. We actually looked at this last week. So when we look at this function, we actually have two different functions and two different loops here. We have two for loops, and they're independent of each other. And so what we do is we just take the value changes. So it's n that is what changes that controls the loop. And so the first one here is the for k equals 1. We have our n is divided by 2, and then on the for j, that one is n squared. So we came to the conclusion that what we care about is that repetitive operation. So each one of those for loops just has one executable statement in it. And so we care about these large values of n. We talked about how we don't care. Really, when we do the evaluation of Big O, we drop it in constants because constants never change. And then when it comes to, we have that function 4 times n squared plus 3 times n plus 10. So we drop that 10, that plus 10, because it didn't really add. Because it's just a constant. And then relative to the n squared versus the n squared had a bigger impact with n change. Whereas n itself, that just was more linear. And then we have the multipliers for each one of them, the 4 and the 3, and we really didn't care about those because, again, they're just constants. So now we started looking at code instead. And what we care about is how often something is going to be executed. And so when you're looking at a for loop such as here, so the sum equals sum plus 5. That's that operation we want to know how many times is it going to execute, and that delta is equal to delta plus 1. So when we look at that here for those values of n. So what we did was, because we had two loops, we had to take them both into consideration. And so the first loop we had the sum equals sum plus 5, and the second loop we had our delta equals delta plus 1. So as a result, what we ended up doing is our total number of operations is just n divided by 2 plus the n squared. So now when you apply the Big O to this perspective, which one has a bigger impact? Well, n divided by 2 is going to just steadily decrease, so kind of like a binary search, whereas n squared is going to continue to increase at exponential value of the power of 2. So So in big O, we look at this and we say that n squared has the biggest impact. So we can estimate that the, n squared is going to give us the most amount of time it takes for those operations to execute. So let's look at this example here. This one's a little bit different. We have a nested loop. We haven't looked at nesting before. So how do we determine in a nested loop which is going to have more of an impact? Or how do we decide what big O is when we have a nested loop like this? So we have our function, and it receives the value of n, and then we just have some incrementers here. And then we have our variable is going to be x is going to be increased by 1. So we have our outer loop that's going to run for starting at the value of 1, and it's going to run until it's less than or equal to n. And then we have our inner loop, which also starts at the value of 1, and that one is also going to loop until j is no longer less than or equal to n. Now, if you remember correctly with nested loops, the inner loop has to execute fully before the outer loop can increment by even 1. So you think about it, if we pass in the value of 10, we pass in the value of 10, our outer loop is going to execute 10 times, right? Well, how many times is our inner loop going to execute? 10 times 10, right? So that's going to execute 100 times. So you can look at this, and if you do the math really quick and you just plug in some number, you're like, oh wow, that inner loop is really going to have a significant impact with the value of n, right? So how do we come up with that from a calculation perspective so that we can represent that in big O notation? So when we come up here again, we're talking about those repetitive operations. And so in this case, we have two loops, but they're nested. So one is dependent upon the other. So our outer loop runs n times, and then our inner loop runs n times. But we know that the only operation is x plus 1 is completely dependent upon the outer loop and the inner loop. So if we look at this on the outer loop, when n equals 1, we go to our inner loop. I equals 1, we go to the inner loop, and it runs n times. And it results in n number of operations. We got to plug in that value of 10. As I gets incremented to some value, so if the next value is 2, again, the inner loop is running n number of times. Again, 10. Let's just use number 10 as an example. So for each iteration of our outer loop, that inner loop is running n number of times, so 10 times. So how do we come up with this annotation? And again, we realize that we're doing n times n, right? So the outer loop runs n times, the inner loop runs n times. And so we come up again with n squared, because that's what it is. Because if we look at the code again, if this value of n is 10, this is going to loop 10 times. And for every time this loops 10 times. And we said that we would multiply that 10 times 10, that gives us 100, right? So that gives us our n squared. So let's look at a different one. So this one here has two independent functions. So they're not nested. So like that first example we had, but one of them was n divided by 2 and the second was n squared. So this case here, they're just the same. We have two loops, independent loops, and they both run. Okay. So what's going on? Again, a repetitive operations. We have two different loops, they're not nested. So our first loop is running n times. So we start at 1 and we go up to n. Only one operation happens, and it's x plus 1. And then how many times our second loop runs? Well, again, it starts at 1, and then it goes from 1 up to n, and its operation is x plus 1. So the code with each one of these loops is identical. So they're not nested, they're actually sequential. So our runtime is the order of n. So it's n plus the n this time, because we have two independent loops that are running n plus n. So we really came up with 2 times n, right? Because it's the same thing and it's happening twice. Does that make sense? So when we talk about big O, we drop the constant, don't we? So we don't really care about that too. So when we did the big O, we just end up with our big O is actually just n in this case. So here, this function, we have a while loop. Well, n is greater than 0. We're going to do a print statement, but remember the print statements really don't matter from the O perspective. It's the mathematical computations that we care about. So we care about where n is set equal to n divided by 2. So we have our single while loop. And with this, we can't really just say that it iterates n times n divided by 2, because there's the evaluation there. You have to take into consideration that it's based on n being greater than 0. So it continues to execute as long as n is greater than 0. So how many iterations is that? Well, that depends. Okay, depends how our number is. So what happens here is in our loop, our executable line of code is that last line of code that's dividing our n by 2. And so n is actually half at each iteration of our while loop. And so it ends up running in a log n time. So if we look at that, remember we looked at the different formats of our n, of how n actually is affected. So we have like the constant, we have the linear, we have the log n, we have the log 2n, we have all those different calculations. So we look at what's going on with this code here. So our n refers to that value that's stored in our input. So let's say that we come up with a value of 100. So let's look at it really quick with 100. So we come in here, our value is 100. 100 is greater than 0, so we're going to go ahead and do the calculation. And so we have our 100 divided by 2. So our n becomes 50. And then 50 still is greater than 0, so we do that again. So now n is going to be 25. And 25 is still greater than 0, so we're going to do that division again by 2. So 25 divided by 2, you end up with 14.5. No. 12.5. Oh my God. There are days. 12.5. Well, we're going to drop the 0.5, right? So we just end up with 12. Come in here, 12 is still greater than 0. Divide that by 2, so we do 6. And then divide that by 2, and we get a 3. Divide that by 2, and we get a 1. And so we divide that by 2 again, and that's when we're done. Okay, so when we come in here, first time through, we get that 100. Second time through, really, it just gets divided by 4, right? Because you divided by 2 the first time, you divide by 2 again, so that gives you a 4. Next time through, you divide it by 2 again, you get that 8. So what's happening here is after the 3 iterations, really your n is being divided by 2 to the 3rd power, because 2 to the 3rd power is 8, right? So when we start looking at this, it's really 2 to whatever the k there. The k is going to tell us the number of iterations that's going to get us it. And so when we end up with this, again, we end up with that 1. Okay, so when we try to divide that 1 by 2, then we ended up no longer getting a true result with n being greater than 0. So we really are trying to solve for that k. How many iterations is it going to take? We can do it in our head. We can do a really quick application that shows us how to do that. But we're trying to find that value, that k right there. And so now, if we go back and we think about our log options that show us how we can do that, we solve for k. So our k is actually the log of the n value that we got, and so our big O ends up being log n. And when we look at the previous lecture on big O, so again, you look at the different options that we have here that are really, really common that we deal with, okay? And then if we look at the definition of the log n, right here, you see that when you're dealing with doubles. So in our case, we're actually dividing by 2 instead of multiplying by 2, but it still gives us that log n. Okay, so we have this next one here, and we have while our I is less than n, we're going to have a loop, and then we have an inner loop. So we have an example with nested for loops. This one is nested while loop. So while j is less than n, and we have this array that's being passed in, and if the value at position I and j is equal to 1, we're going to increment our j. And then after that, we implement our I, and we're going to keep looping until both of these while loops evaluate as false. So when we look at this code, we have 2 nested loops again. So in this case, they're whiles instead of fors. And then, so lots of times when you see nested loops, usually you're going to end up with an n squared is your big O. But you need to actually do a little more evaluation to make sure it really is n squared. So our I and our j obviously are incrementers, right? We have our incrementers here, these are j and our I. And neither one of them ever gets reset to 0, and they actually never decrease. So that our outer loop will end when I gets to n. So once I equals n, we're done with that one. And then, so in that case, our statement I plus, it can never run more than n times, because that's the controlling, that's our condition that stops our while loop from running. And so n is being passed in, so we want to make sure that we don't go past that with other iterations. And the same thing is happening with j. J cannot run more than n times, because once j equals n, it's going to exit that while loop. So the most number of times that this can actually run is n. So if we have the value of 5. Let's say we get the value of 5 here. And so once I gets to 5, we're done. Once j gets to 5, we're done. So it's really this 2 times that n is the number of loops. And so when we're looking at big O, we will drop that multiplier, the constant of 2, because it doesn't have a significant impact on n. And so we end up with just the O. So the O of n is our big O for this example. So here, there is a slight difference between this one and the previous one. So if we look at this loop here, we have our while I is less than n, while j is less than n, and the array value is equal to 1. So we come up here, while I is less than n. Here, our j gets reset to 0. So that changes it, right? If it gets reset to 0, this is going to make it very similar to this nested for loop. Because for every iteration of I, j gets reset to 1, right? We're tracking that? Okay? So that's what's going to change this while loop here from the first version to the second one. This version, our j never changed. This version, for every iteration of our while loop, our j gets incremented. So this is behaving just like those nested for loops did now. Does that make sense? Because it's resetting our j every time. So that makes our while loop on our inner while loop have to execute. Let's say we come in with a value of 5. So our outer while loop can execute 5 times. For every iteration, our inner while loop is going to execute 5 times. Actually, 4. But, not 5. So now we actually get that n squared. Does that make sense? because you have your n times n. The outer loop executes n times, and for every iteration of that, the inner loop executes n times, and so you multiply them together, and you end up with an n squared on that. So that reset of j right here for every iteration of I has a very significant impact on the actual big O representation of this. So here that difference, that resetting of that j to 0, to make that inner while loop execute starting it from 0 to n every single time, we end up with our big O being n squared. So here we have an outer for loop, an inner for loop, but a condition that is executed to determine whether or not, a condition that's evaluated to determine whether or not that executable code is actually performed. So here it's kind of weird. This one is totally different. We have our int A, we have an array, and we have a size for that array. We have an array B, and we have a size for that C. And here we have our looping variables, our I and our J. And so we have our outer loop starts at 0, and it loops for until I is no longer less than size A. And then our inner loop is starts with J at 0, and it continues to loop until J is no longer less than size B. So we don't have a common variable here. We don't have that n, right? Like all the other examples, we had n for both of them, and it was really easy to figure out what was supposed to happen. And so then we check to see if in our array A, if our I is equal to the value in B sub j. And so we have these two different arrays, we have two different looping variables, and we have two different control variables on when our loops stop. So this one is kind of strange, so how do we determine this? We have our runtime here, there's no n in this case. It's like, okay, so now what do you do if you don't have an n? But, all is not lost, we still have our control. Our control is size A and size B. Those are the two things that control whether or not our condition is going to evaluate true or false. And so it's really very similar to our example 2, where they're both n instead of a size A, size B. And so our outer loop runs size A times. And for each iteration of our outer loop, our inner loop is going to run size B times. So that algorithm ends up being a size A times size B. So we can just go ahead and plug this in, because that is our big O. Whatever size A and size B are multiplied together. So this function is similar to the last one, but it has a little bit of a difference here. So here we still get our arrays, our A array and our B array. We still have our sizes, our variables, size A and size B. So again, we have our loops. Our outer loop is a for loop, and so that is size A. It's controlled by size A. Our inner loop is an if statement that calls another function. So for each iteration of I, this function is being called. And the function is called binary search. It's going to pass to array B. It's going to pass the size of B. And it's going to pass position I, or index I, the element that exists in our array A at that position. So, wow, how do we come up with a big O on that one, right? So first of all, we have this function call, and you have no idea what that function looks like. So you're like, well, how can I come up with that evaluation if I have no idea what this function looks like? And so here, one of the things we talk about is single binary search will run log n. So again, go back to this right here. So understanding what these different functions do for you. Okay, so we have our different functions listed here on the left, which are our most common ones that we experience with big O. And then we have our definition of each one of them here. Where'd you go? There you go. So log n. Again, log n is associated with binary searches, with having, with doubling, all of that. So any algorithm that has the data remaining to be processed in each iteration of a loop will be a log n for big O. Okay, so this is just one of those things you need to know this. So when we look at applying that, so here we look at our function call. It's kind of obvious that it's bin search and probably binary search, so you can kind of apply that implication. So binary search is run in log n, because that's the definition of it. So here, n is going to represent the number of items that you are searching. So when we look at this loop, our for loop executes size 8 times, right? And then for each iteration of that, a binary search is being ran, which is log n. Well, that log n, our n value, is size b, because that's what was passed in. When we look at that function again, this is how many times. This is what it's going to do the binary search the number of times. Here's our array. This is how many times we're going. This is the variable that is going to control it, and this is the value we're looking for. So when we come up with our big O, we have our side A. We know that we can use the side A because that's controlling that outer loop. And then we multiply times our log n. We know binary searches does log n. What's the n value? Well, the n value is that size b. That size b is what is controlling the number of times to loop through that binary, that array. Okay. So holy crap, how much more can there be of this stuff, right? Alright, so we looked at the basic concept of big O. We started looking at some different functions and trying to apply it. So there's actually a little bit more to this stuff. This is what's going to lead us into our summation. So we have our big O. We have these two loops, seen this 3 times now. Alright, so we say that the outer loop runs, our first loop runs n divided by 2, our second loop runs n times n, which is n squared. You add these two together, you get the n divided by 2 plus the n squared, and we come up with the fact that our iteration is going to be, our big O ends up being the n squared because that's the most significant impact. Now, if we do this from a summation perspective, what the format would be in this fashion here. So we have our n divided by 2, okay? And we're adding that to our n squared. And so our k equals 1 and our j equals 1. So our constant value, our 1, is inside each summation, and it refers to the one operation in each loop. So here, see the 1 and the 1. So there's that one operation in each loop. And that's all that's happening in each one of our loops. You just have, in the first one, the sum equals sum plus 5, and the second one is delta equals delta plus 1. So that is represented here with the 1. So now we just solve our summation. And so when we solve our summation, we end up with our n with our multiplier k, that k representing the number of operations. And so that equals k times n to come up with our formula here, and our I is equal to 1. So if we do the math, we end up with our n divided by 2 plus our n squared, and then as a closed form solution of this summation, we come up with our big O for our running time. So let's look at this one. We already looked at the code, from a big O perspective, we're just kind of looking at it, go, yes, this is a big O. Now, how do we do it from a summation perspective? So here we have our two loops, we have our nested loop, and again, for every iteration of I, the inner loop runs n times. So we end up with that n squared. So how do we do this from a summation perspective? So we start with our big O and our running time of our code fragment. So again, we have two loops. Outer loop runs from I up to n. Inner loop runs from j up to n. And the only operation really is that x plus plus, right? There's that single operation in there. So how many times does that x plus plus happen? So if we set it up in the summation format, and we want to solve for it. Again, here's our formula. Over here, we have our, whatever our n is, and then our value I starts at 1, and it iterates for our number of operations is k. So in this case, our number of operations is 1, and then that gets that equal to our k times n. So we start with, over here, we have our n, and our I is equal to 1. And then we have our n, and our j is equal to 1, and then that's where we put that operation, is right here on the second one. Because if you look at this code, there is no operation to identify specifically with the I. The only thing that I controls is how many times the inner loop is executed. And so the actual operation, the x plus plus, is right there with the j. So when you annotate that in your summation, that's why the 1 is only associated with this summation and not with this one. So as we do the multiplication on this, what we end up with here is we apply our n, here's our n, and then we do end up with our n squared. So that is our big O. So again, there's that closed form solution of the summation ends up being n squared because that is how many times that loop has to actually execute in order to do the x plus plus inside of the function. So again, here's another big O will end up being n squared, right? Because again, we come in here, we have our n. So the only difference between this one and the last one is this is the sum plus plus versus the x plus plus. Oh, I'm sorry. This one is, I apologize. This one is n squared. Okay. So here our outer one runs for n times, but the inner one is running for n squared. So if our value is 10, for every 10 times the outer loop runs, this one's going to run for 100. Does that make sense? So that ends up being 10 times 100. 10 times 100 is 1,000. So this actually will happen, that sum will be 1,000. Does everyone agree with that? Okay. So let's look at this from a summation perspective. Here's our outer loop. Here's our inner loop. Okay, so our outer loop has our n, and we look at here, so our value of n, when n comes in, because we started the value of 0, it really runs for n minus 1, right? And then the j is the same way. So here, our n minus 1, because we started at 0. If we look up here, see that value was 1 instead of a 0? So because this value was 1, that's why it runs for n times. This time we're starting with 0. We have to take into account the fact that we're starting with 0. So that 0 affects the value of n. So you really are doing n minus 1 up here. Because our incrementer I starts at 0. So then here is the same thing is true. We run until n squared. But because our incrementer starts at 0, we have to do the minus 1 on the n squared. And then here's where the actual operation happens on the inner loop. So if we multiply this together, we end up with our n minus 1, because our incrementer starts at 0, our n squared. And so that ends up with our n squared is times our n minus 1, So we have n to the cube. So what we did is we just applied the above formula twice. And so that gives us our n cubed. Because of the fact that our inner loop is n squared, and then that is multiplied by the outer loop of n. And so when you multiply powers, you actually add them, right? So if we multiply n squared times n, we get n to the third. True? Okay? So that's how we end up with n squared on this. Look at this again. This is n squared times n, so that gives us n to the third times of this run. So if it comes in as a 10 cubed is 1,000, correct? So that's how we end up with that value there. So when we do it from a summation perspective, because these are multiplied, we have our n minus 1, so it starts at 0. N squared minus 1 because it starts at 0. And then when we do the math, we get our n squared here, with our I is 0, to our n minus 1, okay, because that's the most significant impact of the inner one here is n squared. And then as we multiply that through, we end up with the n cubed, because any of our constants, we drop all of that. We don't care about the minus 1, we don't care about the multiplier of 1, we drop all that from a big O perspective, because the biggest impact is n increasing, right? And n being cubed has much more of a significant impact than minus 1 and times 1. So here we want to, so this is getting more into asking you to write an actual summation. And so this is something else that's part of the foundation exam. So here we want to write a summation for the number of multiplication operations in this code. So here we have two loops. And we really pay attention to our bounds on this one, okay? So here we have our number is 0. And so we start at the value of 100. And we're going to loop until 2 times n is no longer, until I is no longer less than 2 times n. And then our inner loop is different. This one is going to loop for until j is no longer less than n squared. So if we look at this, we're like, okay, and then look at the mathematical computation here. So our number that our mathematical computation here is big numbers plus equals I times n is j plus j times n. So if we have a value of 10, our outer loop will execute 20 times. And then here on our inner loop is, well, that won't even work because 100 is not less than or equal to 20. So it actually have to come in here with a value of at least 50 for this to even happen, right? All right, so again, we have two different loops. So this one is kind of really crazy. So our bounds here, our I runs starts at 100 up to and including 2n. Our inner loop starts at 1 up to and including n squared. So now we have to look at the different multiplications to determine how in the heck we're going to come up with summation. So our problem specifically said, describe the number of multiplication operations that are going to be executed based on the controls of our bounds. Okay, so our base number is plus equal I times n, and our j times n. So there's actually two multiplication statements in this. Before this, everything that we've done had some single mathematical computation in it. Okay, plus plus, plus plus, here just addition. So this one is actually different because it has two multiplications. So remember, when we care about big O is the number of executions that have to happen from a mathematical perspective. And so if we look at that, there's two multiplication operations in this one. So how do we write the summation that actually describes this? All right, so first we need to express our multiplications in a form of summation. And so our loop happens, here's our first one, here's our outer loop. It processes 2 times n times, and we start at the value of 100. And then our second loop, our inner loop, that one executes n squared minus 1. Why is it minus 1? Okay, so we have our n squared minus 1. And then that one, look at the value that's here. It's a 2. So everything else we've looked at so far was a 1, right? There's a 1, here's a 1, there's a 1 on this one and this one. But in this case, we have a 2. And the reason why is there's 2 multiplication operations going on. So here's 1 here, and here's 1 here. And so that's going to affect how many times it has to process from an efficiency perspective. So then if we come up with a closed form solution of this summation, so because they're nested loops, it's multiplication. So we have our n to our 2 times n with our I equals 100, our n squared minus 1 with our j equals 1, but that multiplier is actually a 2 now because it has 2 mathematical computations going on in that single statement. And so when we do the math on this, so we start here, we have our 2n with our 100, our I100, and we have our 2 times n squared minus 1. And then, so that ends up being 2 times our n squared minus 1, and we multiply that times our 2n with our I equals to 100 times 1. And so if we break that down, we end up with a 2 times n squared minus 1, and then our 2n minus 99. And so that ends up being our final solution here is the summation, which just shows the number of multiplications that's actually going to happen here based on this loop. So again, when you're talking about the big O, you're talking about where is the impact. The impact is on those executable statements. It's not on the looping itself. It's on the executable statements. This is the executable statement. This is where the efficiency is going to have an impact. How many times does that right there, how many times is the big number plus equals our I times n and plus our j times n? How many times does this have to actually execute? That's what we're solving for with big O, is how many times does this right here execute? And the reason why in this situation you have that multiplier 2 instead of just the 1 is because you have 2 multiplication procedures being done here. It's not just the 1. Everything else that we've done up to this point only have like a single statement in there with the plus plus or doing the sum is equal to sum plus 1 or delta is equal to delta plus 1. So are you sufficiently overwhelmed with big O? Yeah. Which one? Okay. Yeah, I see that. You are asking a question correctly, and I'm looking at that and I'm going, yeah, that doesn't make sense. correct that this is a typo, but absolutely positively make sure. But I think you're correct thinking that that -1 should not be there. Because, let me look at that. It's less than.
So you're running it n squared times -1. You could running it when j is equal to n squared.
Bear with me. So this is less than or equal to. So that ends up being n.
Because you zero in that.
Well, this one makes sense because of the 0,
Yeah.
but it's less than
Yeah, so it should still be n squared.
-1.
But you start at 0. That's why it's still n squared.
But then,
If you started at 1, it would be n squared minus 1.
but this one is 1, but it's less than
Yeah, so that one should be n squared minus 1.
because it's less than, not less than or equal to.
Because it's less than and because we're starting at 0.
But the -1 was based on this starting at 0.
Yeah. Think
Say that
about it.
again?
Less than 5, 0, 1, 2, 3, 0, 1, 2, 3, 4.
Right.
And you have 5 elements.
Mm.
So you start at 0. So if you do starting at 1, that's 1, 2, 3, 4.
If it's less than,
Yeah,
but
so yours will be minus 1.
here, if it's less than or equal to, you don't do the -1.
I mean, to tell you the truth, it only really makes a difference when you use the identities and you expand it. So either way, you should kind of come to the same answer, mathematically. Because when you do the identities, there's 3 different cases. There's a case where you start at 0, a
Yeah.
case where you start at 1, and a case where you start at some arbitrary number.
Okay.
So regardless, so even though you might use different math, you should always come to the same answer. Because the identities won't change.
I don't need a better explanation. Okay. Yeah, right. I believe that the reason it's less than 1 is because of the left hand, which is the reason why it's -1 is left hand versus left hand or equal to, because the left hand or equal to can add 1 to it, right? And they can run one more time, right? Whereas the straight up left hand here, it doesn't matter that it's 0, it's still less than. So that's how you end up in the -1. You always end up with n -1. That's the one thing about it. They take 1 to a very small thing. But I'll absolutely positively confirm that to make sure that